I'll talk about uh, more broadly about the work that we have been doing in the area of deep learning in generating some novel deep learning algorithms, specifically using differential equations. But before going into the research, maybe I will talk a bit about the collaboration that we are having with RIKEN AIP. And for last few years, we have been collaborating with RIKEN AIP. And it all started uh, in 2018 when I visited Japan as a part of Sakura Science Exchange Program, and also happened to visit RIKEN AIP during one of the days during this Sakura Science Exchange Program, and could meet Professor Masashi and Dr. Imtiaz. So these collaborations then started growing further and further after this visit to RIKEN AIP. So in 2018, JICA, the Japan International Cooperative Agency, started some program called Collaboration Kickstarter Program to kickstart the collaboration between the IITH researchers and Japanese researchers. So I, along with Dr. Imtiaz Khan from RIKEN AIP, we submitted a proposal, and we got this funding for this proposal on Bayesian deep learning. And with the help of this proposal, I was able to visit, with funding from JICA, I was able to visit RIKEN AIP multiple times during 2018 to 2019 until the COVID period. And there were several student visits also happened during this time, which was thankfully supported by RIKEN AIP. And following these, we had several other initiatives happening between IITH and RIKEN AIP. For instance, we signed the MOU between IITH and RIKEN AIP in 2019. And also at the same time, we organized this joint workshop between RIKEN and IITH and RIKEN AIP. I hope a few of you may be already part of that workshop also. And as already mentioned by Professor Masashi and Dr. Vinny in their talks yesterday, one of the major outcomes of this is the organization of this Asian Conference on Machine Learning for the first time in India at Hyderabad in December 2022. We still continued our collaborations with RIKEN AIP, and JIPA proposed the second program called JICA Friendship 2.0 Research Program. And along with Dr. MD, we submitted a proposal on Bayesian causal learning, and which is again got approved. And using these funds, I could visit again RIKEN AIP multiple times during 2024 and 2025. And the student visits were also supported by JICA at this time. And Dr. MD organized these Bayes duality workshops for past couple of years, at least 2-3 years, and I could attend this workshop in June 2024 and 2025. And yeah, now we are having the second joint workshop on AI between IITH and RIKEN AIP. So this is just to give an introduction of how, apart from whatever funding that RIKEN AIP provides, the possibilities of having some joint collaboration between IITH faculty and RIKEN AIP researchers. Okay, so maybe now I will move on to the research part. Yeah, so my group at IIT Hyderabad, which is known as Bayesian Reasoning and Intelligence Group, BRAIN Group. So we work in different areas of AI. We do some work on the applied areas of AI, like natural language processing, computer vision, and core AML areas. Some interdisciplinary work on astrophysics, on mechanical engineering problems, etc., and some industry research. On core AML, we work on problems such as continual learning and unlearning, bringing learning capabilities into systems, which adaptive learning capabilities into systems. And then we do some work on developing deep learning models-based differential equations, as well as the reverse of that, like solving differential equations using deep learning models, which in general is known as physics-informed neural networks. And we also do some work on causal learning, Bayesian deep learning, etc. So in general, we aim to develop some novel deep learning models, which are parameter revisions, which can learn with limited amount of data and are robust and capable of modeling uncertainties, have some reasoning capabilities, and also quite adaptable, can continuously learn without forgetting, can unlearn data, etc. So they could be quite useful in very high risk and data scarce applications like healthcare, autonomous navigations, etc. So in today's talk, I will focus on one specific area that we are working on in the intersection of differential equations and deep learning, and how we can develop deep learning models or novel deep learning models based upon differential equations. So this area in general known as the neural differential equations. Perhaps one of the paper which made it quite popular is the neural ordinary differential equation paper, which appeared in Neurons 2018. So the general philosophy is to develop deep learning models, continuous deep learning models based upon differential equations. And it could be quite useful in bringing parameter efficiency to deep learning models to improve their model selection process, and also robustness to address robustness to a great extent. So in our work, we make use of differential equations, deep learning philosophies, Bayesian learning philosophies to come up with novel models, and which is capable of achieving these objectives. So this is overall some a broad idea of different works that we have done in this area of neural differential equations. So we worked on ordinary differential equations, specifically using these ordinary differential equations to solve supervised learning problems, image classification problems, and text classification problems, etc. And we also developed novel models based upon partial differential equations. And specifically, they have been used to model irregularly sampled sequence data. And on application side also, we have done some work on astrophysics, test classification. I collaborate with a faculty professor, Shantanu Desai, from physics on astrophysics, and he'll be giving a talk later for this workshop. So today I will be focusing on a couple of works that we have done in this area, one using the ordinary differential equation and another one using the partial differential equation. So before going to that, I can give a brief overview of what the neural ordinary differential equations are. Yeah, so this is something we are all familiar with, residual networks, which became quite popular for image classification and related kind of works. And the main idea is to make deep learning models capable of learning without facing any vanishing gradient issues, etc., by having a skip connection, which is like a direct connection to a previous layer. And consequently, the hidden layer transformations will take a form like this, right? So this is the typical transformation that we have in the case of fluorescence, where the hidden layer at layer T+1 can be seen as equal to hidden layer representation at previous layer plus the transformation, the ResNet blocks. But a very interesting observation is that, and if you go for, so basically if you look at this equation, we can see that, okay, this is very similar to solving a ordinary differential equation. For instance, if you consider some ordinary differential equations like this, dHt by dt is equal to f of ht. And if you consider some numerical method like Euler's method in solving this differential equation with step size equal to 1, then we exactly get this transformation that we have in ResNets. So this is a very interesting observation, and this was something which has made this neural ordinary differential equation paper quite popular. And we can have such kind of ordinary differential equations to represent deep learning models, in fact, parameterized by some neural network like the ResNet blocks. So what we have here is a ordinary differential equations parameterized by f theta, which is a ResNet block, leading to these field of neural ordinary differential equations. And we can see that they will result in some kind of a continuous transformation of the hidden layers. So we consider this input image or some representation of the input image as the initial value, pass it through this ODE solver until some capital time t, and we'll get a final representation at time t, which is used for doing classification or regression, whichever task we want to solve. So this is the general architecture of neural ordinary differential equation. So even though it could overcome some of the drawbacks, model selection, parameter complexity, it still has some issues. For instance, this complexity will depend upon the time until we want to run this ODE solver, the capital time T, which implicitly determines the number of transformation or depth in some manner. So we would like to further improve this model selection capabilities in neural ODs and also bring uncertainty modeling capabilities. So based upon this, in order to achieve this objective, we propose these latent time neural ordinary differential equations. The idea behind this latent time neural ordinary differential equation is to treat the time t until which we want to run the ODE solver as a latent variable and learn that from the data. So we assume this t to follow some distribution, and we would like to learn that distribution from the data given to us. So if we know this distribution, we can sample t, and for different values of t, we can compute the final hidden layer representation, and we can compute our final output based upon all these hidden representations associated with different t's that we sample from the distribution. So this will result in some kind of an ensemble kind of an approach, which will be capable of modeling the uncertainties in the model as well. So on the basis of this idea, we propose two approaches. One is known as the latent time neural ODE, which learns a global distribution over T for all the data points, while we also propose some adaptive latent time neural ODE, which learns the distribution over T, which is specific to each data point. So here we have a distribution over each of these TAs associated with an input xi, and we will soon discuss how we are doing that. So to learn this distribution over T, we follow a Bayesian approach, where we assume some kind of a prior distribution over T, and then the ability to model the outputs for that given T is computed in the form of the likelihood. And then we use this, the Bayes theorem to combine the prior and likelihood to obtain the posterior distribution over T. And of course, in this case, the posterior cannot be computed in closed form. So we use a variational inference technique, where we assume a variational distribution over T, which is assumed to be a gamma distribution with parameters alpha q and beta q. And we learn these variational parameters by using the variational lower bound or evidence lower bound. So the evidence lower bound is given here, and we maximize this evidence lower bound with respect to these variational parameters as well as model parameters. And we learn the distribution over T. So this is the idea that we have for the latent time neural ordinary differential equations. For the adaptive latent time neural ODE, we would like to learn a separate distribution for each input. So if you consider parameterizing it with respect to every input, for instance, we assume that it has a separate gamma distribution for every input, the number of parameters that we want to learn will grow linearly with respect to data. So this may not be very helpful. So we went for a amortized variational inference technique, where we assume that these variational distribution parameters for every data point can be obtained as a function of the input. See, we assume there's a neural network. We pass this input xi to this neural network, and it can produce as output the variational parameters associated with every data point. Now we can form a variational lower bound based upon this, and we can see that it is going to be a function of this neural network, which generates these variational parameters, as well as the function of the the neural ODE model parameters, and we learn both these network parameters by maximizing this evidence lower bound. Yeah, so basically this is the idea. So there are some additional things we have to take care of in computing the evidence lower bound, etc., which is discussed in the paper. And we also conducting experiments to see how well we are able to recover the T, and we could find that the model are able to recover the T accurately. And also we conducted some experiments on uncertainty modeling. And we found that, okay, for instance, this is the graph where the red region shows the region where we have some observations, some training data regime, etc. While this region that you have in between, we don't have any observations, we don't have any training data. And these models were able to model the uncertainty in these regions better than some baseline models. So we conducted several experiments to study the generalization capabilities, uncertainty modeling capabilities, robustness capabilities. For instance, in the case of out-of-distribution data modeling capability, we found that the proposed models are having a very good uncertainty modeling capability, able to give a very good average entropy compared to the baselines. Now, so even though the neural ODs were useful for such kind of supervised learning problems, they can be more effective and useful for problems which involve some irregularly sampled sequence data. Okay? For instance, if you consider social media, people will be posting about different views in social media, and their posting will happen at irregular time. It doesn't happen at regular intervals of time. And also, if you consider some devices which collect some information about some humans, okay, for instance, some devices would collect some information about SpO2 or heart rate, etc. Maybe they will be collecting at different time periods at irregular times, or maybe some of the data at some regular intervals could be missing, and because of that, there could be irregularity. But there are several instances where the observations are not seen at regular intervals, but irregular intervals of time. And for such kind of a sequence data, many times we use RNN-based models, but the RNN-based models might end up ignoring this kind of irregularity in the time intervals where we observe things. And we would like to capture that also and consider the hidden transformation exactly based upon the time differences between two consecutive observations. And this is where the neural ODEs can be useful, where you can model the hidden state evolution over time as a neural ODE. For instance, we can consider a neural ODE transforming the hidden state at time ti to a hidden state at time ti plus 1. And it can exactly take care of the time difference between these two observations from ti to t plus 1 in computing the hidden states. So we have developed some models based upon these for text classification, for social media text classification, etc. But we observed that the existing, those kind of models, which we can generally call as recurrent neural ODs, they consider these continuous transformation of the hidden states over time, but the depth is still considered discrete, and the number of such transformations is considered as discrete. That fixed depth can restrict the representation learning capabilities. For instance, when we conducted some studies, as we can see in that figure on right-hand side, we can see that as depth increases, the models are able to achieve some performance which is close to the ideal performance. So many times we don't really care about that depth, and we may fix it to 3, 4, 5, etc., which may not help us to achieve the ideal performance. So if we can bring these model selection capabilities in terms of the depth also into these kind of recurrent neural ODs, which can help to improve our representation learning capabilities. So based upon this idea, we proposed models which treat depth also as a continuous dimension where the hidden state evolves continuously over both time and depth. And when we consider such kind of a model, it can resemble some kind of a partial differential equations where you have a hidden state which is a function of both time and depth, and there is a equation governing how it evolves over time, and there's an equation governing how it evolves over depth. So these kind of models we call as continuous depth recurrent neural differential equations, and we found them to be very useful for these irregularly sampled sequence datasets. So we propose two specific kind of models. One is based upon a heat equation, which is a partial differential equation, and another one is based upon wave equation, which is another partial differential equation. And we have developed the neural PDs based upon this heat equation, which we call as neural heat equation, and based upon wave equation, which we call as neural wave equation. And we found that these two different models exhibit different behaviors. The interactions they capture is slightly different. And in fact, we found this neural wave equation to capture more richer interactions and give a better hidden representation than a neural heat equation. And these some of the works that we have done recently. One of the works appeared in the IC Lab 2025 is based upon this neural wave equation. Yeah, so when we look at these experimental results on some of these benchmark data sets that people use in this area, like pocket 2D person activities, sepsis prediction, etc., we could find that the neural wave equations is consistently giving a better performance than some baselines models, as well as neural heat equations. And in our observation, we find that, okay, they can model much richer interactions and give a much better representations than the standard neural ODEs or RNNs. And that can help in model selection to a large extent. We don't have to specifically choose the depth. It can automatically determine depth depending upon the complexity of the data set. And this physics-informed inductive bias can be helpful for some specific areas in science and engineering discipline. It can help us in discovering some PDEs for some problems arising in science and engineering domains. Yeah, so maybe I'll stop here the talk for today. And thanks a lot. Arigatou gozaimasu. If you have any questions, please feel free to ask.
Yeah, thank you for the great talk. Yeah, audience, if you have questions, you can speak by unmute yourself. Okay, may I ask a question?
Sure.
Yeah, so I think you have a when you compute the posterior distribution, you have another neural network to mapping the data to the posterior parameters alpha and beta. I'm wondering what's the purpose of this neural network? Because in Bayesian inference, usually we can just maximize the lower bound to learn the parameters. Why do you need this additional neural network?
I see. So here in this specific case, we are learning a separate distribution for every data point. We assume that the TI, the distribution over the time, is going to be different for every data point.
Yeah.
And if we consider this setup, then the number of parameters that we want to learn is going to be very large, and it will be not 2 times the number of data points. So we want to overcome this complexity by having a neural network trying to predict these parameters instead of learning these parameters repeatedly. So instead of learning each of these the parameters for every data point, we just need to learn these neural network parameter 5, which
Okay, I see.
as the input and map to these specific parameters associated with xi, alpha QA, and beta QA. So that's the advantage.
Okay. Yeah, I understand. Yeah, thank you. Yeah, MT, please.
Yeah, I have a question. In the previous slides, you had the posterior distribution over T, right? So I was trying to understand what kind of uncertainties is this trying to capture, or is it enough to do this, only this?
Yeah, the kind of uncertainties it tries to capture, we expect it will be capturing the epistemic uncertainty to some extent, but we don't know like if it is sufficient. It is basically, it is trying to capture the uncertainties based upon the depth, based upon the representations at different depth, if you look at it from a discrete point of view. And maybe it may not be as good as capturing the uncertainty based upon the distribution over the parameters.
Yes.
That could be a much better way of modeling uncertainties.
Yeah, I was wondering if somehow they're related to each other, and that would be very interesting because it seems
that would
like
be
it
very
should be. Yeah.
Yes. Yes.
Okay, thank you.
Thank you.
Hello. Do you have time for another question?
Yeah, please.
Okay. Well, thanks so much for the nice talk. And yeah, I mean, I'm not so familiar with neural ODs, but some time ago, I read a paper on this like second order optimizers for neural ODs. That was like, I think a NeurIPS paper or something. And then they kind of use again the optimal control principles to suggest that you can also optimize the time t, right? Capital T. Are you aware of that work? And in particular, does it work well? And I think it could also be used with this uncertainty quantification that you're doing here.
Yeah, maybe I am not explicitly aware of that work, but I do see that some control over number of function evaluations can be done based upon the error, the tolerance value associated with the solver, and that also can be a way to model uncertainty. But then instead we decided to go with a distribution over T rather than over that tolerance, because I feel that tolerance is an important parameter we shouldn't just play around with, as we want to keep the tolerance level to be as small as possible. So in terms of some design choice, okay, this is something we have, but specifically on that work, I'm not sure.
Okay, thanks.
Okay, thanks.